Have you ever marveled at a self-driving car navigating the roads, seemingly making decisions and avoiding obstacles with ease? Today, we're unpacking the hidden science behind this technological marvel, shedding light on how these cars perceive, think, and act autonomously. To truly see the world around them, autonomous cars rely on three primary senses, each providing a unique perspective. First, there's LiDAR, which stands for light detection and ranging. Imagine the car emitting rapid pulses of laser light, firing them into the environment at a rate of millions per second. These laser beams travel outwards, carrying information about their source, be it a pedestrian, a lamp post, or anything else on the road. Upon hitting an object, the light gets reflected back to the sensor. Now, LiDAR works its magic by precisely measuring the time it takes for these echoes to return. With this information, it creates a detailed three-dimensional model of the surroundings, allowing the car to perceive distances, shapes, and even textures of objects in its path. Next, we have radar, a tried and true technology that has been part of our weather forecasts for years. Unlike LiDAR, radar uses radio waves instead of lasers. This method is particularly adept at gauging distances and velocities, offering insights into both where things are and how fast they're moving. It's especially useful in less than ideal weather conditions such as fog, heavy rain, or even when dust is in the air. Unlike LiDAR, whose range is limited, radar can see much farther, helping the car anticipate what's up ahead. And finally, we have cameras, the eyes of the car that capture visual information just as we do. Cameras are crucial for tasks like reading traffic lights and road signs, observing pedestrians, and recognizing other vehicles. While cameras alone cannot measure distances as precisely as LiDAR or radar, they excel at interpreting what we see, giving context to the data collected by these other sensors. These three senses work in concert, each contributing a unique piece to the puzzle of the car's environment. However, the data they provide is raw, unrefined, and it's here that the magic of algorithms comes into play. Perception algorithms are designed to interpret the raw data from these sensors, transforming it into meaningful information. For instance, they can differentiate a cyclist from a lamp post or a car from a plastic bag, a task easier said than done. Computer vision plays a significant role here, employing pattern recognition and object classification grounded in the physics of light and shape detection. This process involves a series of steps, each designed to extract meaningful features from the raw data. Edge detection, for example, identifies the boundaries of objects, while optical flow algorithms determine the movement of objects and the camera. By combining these insights, the car can build a dynamic representation of its surroundings, enabling it to make informed decisions. But seeing and understanding the environment is only half of the story. Self-driving cars must also predict what's likely to happen next, anticipating the actions of other road users and the behavior of objects in their path. Using Newtonian mechanics and statistical modeling, the system simulates potential scenarios, forecasting the movement of other vehicles, pedestrians, and even the trajectory of a thrown ball. This predictive capability is essential for safety, allowing the car to plan routes that avoid potential hazards or come to a stop before an intersection if necessary. Once the car has perceived its environment and made predictions about its future state, it's time for action. The car needs to translate these decisions into physical movements. This is where vehicle dynamics comes into play, a set of algorithms that govern how the car moves. These algorithms consider the laws of physics, including friction with the road, inertia during turns, and g-forces during sudden maneuvers. Trajectory planning is a key aspect of this, where the car plots a safe and optimal path forward. Kinematic equations come into play here, allowing the car to calculate the necessary curves and speeds to navigate the road smoothly and safely. Finally, the decisions made by the car need to be carried out by the vehicle's actuators, which include the steering wheel, throttle, and brakes. When the car decides to turn, the steering wheel must respond accordingly. When it needs to slow down, the brakes must engage. All these actions are initiated by simple commands: steering, left or right, brake, accelerate, go, stop. It's a straightforward language that the car understands, allowing it to interact with the physical world in a controlled manner. At the heart of these processes are two crucial elements: maps and knowing where you are. High-definition maps provide detailed information about the road network, including lane widths, curb heights, and even the pavement's slope. This is especially important for maneuvers like parking or driving on uneven roads. But simply having a good map is not enough. The car also needs to know exactly where it is on those roads. This is achieved through simultaneous localization and mapping, or SLAM, a powerful technology that enables the car to build its own map while keeping track of its position within it. This is akin to exploring a new city, where you not only want to know where you are, but also where everything else is in relation to your current position. SLAM allows the car to do just that, utilizing sensors like IMAs to track acceleration and rotation, combined with GPS to triangulate its position on the map. In essence, self-driving cars are a testament to the power of combining multiple senses. Through a process called sensor fusion, they integrate data from various sources, interpret that data using sophisticated algorithms, make predictions about the future state of the environment, and finally, translate these decisions into physical actions. As technology advances, the precision and efficiency of these processes will continue to improve, bringing us closer to a future where autonomous vehicles navigate our roads with ease and safety. What do you think? How do you see the future of autonomous driving? Share your thoughts below. Thanks for watching.